So far we have seen some examples in which the object, the rotating object, was itself at rest and the rotation is taking place. So you can apply the rotation formula, torque forces on it, and figure out the unknown physical quantities. Now there is a possibility that both types of motion are present. That object is rotating and at the same time it is also translating. When I use the word translation, do you understand what it means? It's moving in the straight line, at the same time it's rotating. Okay, for example, you have a ball on the inclined plane and then you let it go. We all know it's a ball is going to roll, but at the same time it is moving in forward direction too. So not only rotating, it is translating too. Both motions are present. One motion is related to its rotation, which is if it's going clockwise starting, then omega, you can write omega there, that it's going clockwise, omega would be perpendicular to it, and it should have a center of mass. Every object has a center of mass, okay, regular or non-regular. Every object should have a center of mass. That center of mass would be moving with some speed as well, correct? So it could have two kinds of energy associated to it. It could have a kinetic energy related to its linear motion. It should have a kinetic energy related to its rotational motion, and they all add up. Okay, anything which is not only translating but also rotating, it is taking up a lot of the energy, because the energy, some of it is going to whatever has been allotted to the system, some of it will go into rotational energy, some of it will go into translational energy. Now there are some rules. Motion of the rotation about moving axis. This topic will talk about the similar situation in which not only the object is rotating, it's moving in a straight line too, it's translating too. If this happens, then every possible motion of rigid body can be represented as combination of two motions of center of mass and rotation about center of mass. Okay, so this is exactly what I was talking about. The motion can be combined into, if the object is translating. So center of mass will move and the object itself is going to go about this center of mass. In such situation, the total kinetic energy, so I'm using some abbreviations here. I hope you already know about them. If you don't, let me know. Total kinetic energy can always be represented as sum of kinetic energy of center of mass and rotational kinetic energy about the center of mass. Okay, So basically you have to see how the object rotation is about the center of mass, figure that out, and then the center of mass, if it's moving itself, then you have to put it together with it. So the total kinetic energy in such situation would be given as half m VCM square plus half I omega square. What is half m v square? It's a formula for the linear kinetic energy, right? If anything is moving in a straight line, you will use this formula to represent the speed. So VCM represents the speed of the center of mass, right? And half I omega square is related to the rotational kinetic energy. If you sum them both, that is going to give you the total kinetic energy of any system. Good so far? Does that make sense? Because it's not alone. This time, it's not just rotational, like we saw in one of the problem where the pulley was fixed and you are pulling the rope out, the string out of it, and it's rotating. There would be some situation like that. In that case, you just have the rotational. But if it is translating and rotating, then you have to figure out the kinetic energy about the center of mass plus the kinetic energy on the straight line. Yes?
So this is rotation about a moving axis or above a moving axis?
This is the rotation is about the one axis. That is not changing. That is the axis passing through the center of mass. So rotational axes remain the same. Don't get confused by two different axes. One is the rotational axis, and that rotational axis is moving along a straight line.
So these are like little facts that we have to know. Is it about that moving axis or above the moving axis? Where you labeled it above it?
Rotation about. Okay, Samantha, thank you. There was a typo on the board. Okay, now I see what you mean. Now consider one example. So same example, inclined plane. There is a sphere sitting on the top of it. The height of the center of mass from the bottom, we can call it h here. I can give you numbers later, but the numbers can be provided. This sphere, let's say it has mass. Big M is moving with it's going to move with, here it is at rest. It starts from rest. Okay? Like you put something on the top of the inclined plane, it hasn't started moving yet. But when it is moving, it reaches to the bottom of the inclined plane and it will have a speed there. And it's rotating about the center of mass axis. Good? So center of mass axis has translated to. Correct? It has translated from this point to this point. What kind of energy it has when it is on the top? Only potential energy. Does it have any kinetic energy? No, it hasn't started moving yet. No kinetic energy. So if I start, I'm going to erase this and use this side for the problem. You said mgh, correct? Plus 0, linear kinetic energy plus 0, rotational kinetic energy, right? What I'm trying to do, figure out, write VCM in terms of some known numbers or given physical quantities. Maybe h is given, mass is given, inertia is given, and I want to know how can we find VCM when it reaches to the bottom of the plane. Okay, this is what we are looking for. So using, now kinetic energy is not the same everywhere, but we know that that's energy at point A, that should be equal to energy at point B, which is half mvcm square plus half I omega square. Is that correct? Right? All the potential energy, so it has whatever it had here. Let's say it had 10 joules here. Those 10 joules will be divided between this linear kinetic energy and the rotational kinetic energy. Rotational kinetic energy will be greater or VCM will be greater? Should they be equal? Exactly equal to each other? Exactly equal. So they should both, if it's 10 joules, both should be 5 joules? Not necessarily. The reason is, I will decide how much to take. Okay? If I is greater, then kinetic energy rotational would be large too. Right? For example, let's say with the same mass, you replace this sphere by a ring, like we talked in previous lecture. If I have a ring here, ring is going to have greater inertia. It's going to take up more kinetic energy compared to what it was for sphere. Okay, so it really depends on the value of I, that how much this object is going to take away from this total energy given. So its share could be greater if the inertia is greater. Its share could be small if the inertia is small. Okay, so they are not necessarily equal. Okay, and if you just think that the rotational kinetic energy is not there, would this new VCM be different without kinetic energy rotational? Yes, yes, yes. So, if, for example, if there is no rotational kinetic energy, all of potential goes into linear. If there is rotational kinetic energy, then some of it would go into rotational. It will slow down the sphere. Rotation slows down the object. It doesn't go as fast as it was going. But at the end, it should be converted, everything should be converted to the total energy. But it will slow it down. The speed cannot be the same. All right, so, okay, so from here, we can set them equal to each other. EA should be equal to EB, right? According to the law of conservation of energy, they must be equal to each other. Setting them equal to each other, mgh is equal to half, this is big M, half m VCM square plus half I omega square. Good. Now this, what is bothering in this equation? H does not bother me. Mass also doesn't bother me yet. G, of course not. It's not a problem at all. These two are very different, but they two could be connected to each other. How? Is center of mass or the linear speed, is it related to omega anyway? V is equal to R omega. Replacing that, mgh equal to half m VCM square half I omega VCm over R square. Good? Replacing it, we have also, do I know the I for a sphere? R is the radius of sphere. Do I know I for sphere, moment of inertia of a sphere? Yes. The table I gave you last time, in that you will look at the sphere. Sphere moment of inertia is equal to 2 by 5. Is that correct? mR square VCm square over R square. R square gets cancelled. You have half m VCm square plus 2 gets cancelled, 1 over 5 m VCm square, mgh. See, we have narrowed it down to this equation. Almost gotten rid of most of the quantities which we don't have to know for this. Now you can see m is on both sides. It will be gone, right? It will cancel out. You will have GH is equal to Does that look all right? Right? VCm would be equal to 10 GH over 7 square root. All you need to know is the H. Right? If H is given to you, you can easily find out what would be the speed at the end of that inclined plane. So for example, if H is 10 meter, you can just plug that in here, 10 times 9.8 times 10 divided by 7, and you can find out this value of VCm. All right. So this question put together different concepts. Okay. One concept is when there are two different kind of motions, translation plus rotation, and you also use the law of conservation of energy to find the unknowns. Yes.
Instead of doing that, could you just replace VCm squared with R times omega squared and solve it like that?
If you are looking for omega, yes. It really depends. You can if for example, instead of VCm, you need to find omega for the rotation, which would be the same throughout. You can use the same equation, but this would be replaced by R square omega square. Yes. You will need the if you go by that way, you would need the radius of that sphere. Yeah, you won't be able to get away without.
Solve for the radius and omega time velocity as well.
Yes, yes. It's a longer way, but yes, can be done. Yes, that's not wrong. Make sense? Yes.
I know you said that energy of A and energy of B, wait, did you say energy of A and energy of B equal to each other?
Yes. Total energy.
Because it's law of conservation?
Law of conservation of energy. If the and the plane is frictionless. If the plane is not frictionless, then it may not be true.
So all we're going to solve for the velocity of the center of mass, not rotational kinetic energy versus linear kinetic energy, right?
Say it again.
I know you gave us the two equations for linear kinetic energy and
Uh-huh.
the rotational kinetic energy, but you said they may not necessarily be exactly the same.
They may not be the same, yes.
But we can still set them equal to each other because of the law of conservation of energy?
We didn't set the rotational kinetic energy equal to the linear kinetic energy. We cannot, we don't know what those values are.
But the equations.
But energy, what we can use with confidence is about total energy. Okay? So that was in your quiz too. I think the total energy and kinetic energy, don't confuse them with each other. Kinetic energy could change. It's the total energy of the system that you can always compare with energy at a different point. That would be the same. Okay? Whatever those energies are, they could be potential, kinetic, rotational, linear, whatever they are. But total energy, that would not change. So what we use here, we did not use the idea of putting the kinetic energies equal to each other. We have put the energies equal to each other. Total energy of the sphere.
So we said the energy is equal to each other. So if we move them all to one side, it equals
Yes, yes, yes. So initially the total energy was total potential energy. Finally the energy was total kinetic energy. But you know total kinetic energy in this case was not just the linear. Because it's rolling too. Okay? So because of rolling, it will have a rotational kinetic energy component to it. You still did the same thing. Did you notice you still did the same thing? You did PE plus KE equal to PE plus KE. This is what you did here. Kinetic energy is not alone. It has two components to it. Okay? It's something like what you just, a person jumps on the platform. Platform is mounted on a spring. Spring is compressed. You have gravitational potential energy. At the same time, you have elastic potential energy too. You need to take care of both. Here, kinetic energy is not just the linear. It's both. It's rolling and it's moving. Okay? You remember yo-yo? I'm going to give you a problem of yo-yo, which I don't think I will have time to solve it, but I'll give you that because that is also very good-looking problem. In yo-yo, do you notice it moves and it rolls? It goes down and at the same time it's rolling about its axis too. So that's a great example of a disk which is rolling and translating. Okay, so let me give you a problem. I'll give you some numbers that you can work with at home. So now drawing a yo-yo on the screen, the blackboard is going to be a challenge. Okay, so it has come down. So it's starting from here. This is your reference line. Potential energy is 0 here. Potential energy has some value at the top position. It has a mass, center of mass. That center of mass has moved down to this, and it also rolls. So it's roll this way, omega. And the speed of you want to know what would be the speed at the end of, just the way you did the speed of the speed at the end of the inclined plane. You want to know when it stops, when it reaches to its final moment before it comes to rest, what would be its final speed. You need to use a similar equation that you use here. Find out the energy at this point, find out the total energy at this point, okay, set them equal to each other and find the VCM for this. This height is given as 3 meter. Mass of the yo-yo is 20 grams. And the radius is 0.5 feet. okay, 3 centimeters. That seems more reasonable, even less. And you need to find out VCM at the end. You can call these points as point B and point A, VCM at point B. Okay? Is it going to be very similar problem? What we did on the inclined plane, you're going to end up some equation of 4 VCM here. My question is, which object you are going to treat it as? A sphere, a cylinder, a disc, a ring, what? Disc? Disc is reasonable? Solid disc, right? And whatever number you get, do you think you are going to get a VCM greater or less? Compared to a sphere.
It should be greater because
Yeah.
mass would be displayed or referred to a flat plane instead of already sphere surface.
Yeah, it will be greater. Yeah. You will get 4 by 3. GH. This is what you should get at the end, after all the work. After all the work, okay? The friction, where is friction in this whole process? We didn't talk about it on the inclined plane, we didn't talk about it now, and we know there must be some sort of friction between the inclined plane and the rolling sphere. The rolling friction if the object is moving to the right, the friction is going to be to the left side, and every time, every single point that moves up or that moves down, correct? Because something, when think about the tire of your car, if it is rolling, at one point it goes up and the other point comes down, next goes up, then down, up, down. So they are constantly moving vertical to the horizontal direction. So if the friction is this way, particle displacement is upward or downward, the rolling friction does not do any work. Okay, so even if it's there, it is treated as a static friction. Rolling friction is treated as a static friction. It does not do any work for the rolling. So basically there is no force acting against the object when it is rolling.
So does that mean you would consider friction to be negligible at all?
We don't consider it, yes. There is no friction. But if you have, for example, instead of a rolling ball, you have a box sliding down the plane, friction will play the role. It's not rolling, yes. It's not static friction, it's kinetic friction, and it is going to decrease the net force on this. This is not going to decrease the net force on it. The force will produce the torque. It doesn't mean it's not going to rule. There is no force on it. There will be a force, but that force is going to produce torque on it.
So
friction is not, rolling friction doesn't have any friction. Work related to friction. And the condition for this is Cm must be equal to R omega. That the contact is always made, okay, friction is always there, contact is there, and it's rolling as long as it keeps rolling. Okay, if your tires stop rolling, what happens? The anti-braking system in your car, what does it do? You know, it doesn't let it stops. It does not stop the tire from rolling. It doesn't let it slide, because if it is sliding instead of rolling, it's a kinetic friction. It's lower. That's not enough friction. Car can skid. Have you ever thought about it? Your car tires, they have to keep rolling in order to keep going. It has to maintain the contact with the road all the time so that it does have a static friction between the tires. As soon as it is moving straight or in any direction, it's going to have other friction, which is obviously not, which is less than the actual friction. There will be friction, but it's less. It's sliding, it's not rolling. So there is a misconception about the rolling friction, that it is a kinetic friction, or it's like you can treat it because it's moving, but rolling friction is not a kinetic friction. It is a static friction, because every point during rolling is in contact with the other surface at some point. All right, the last topic of this chapter is the angular momentum. So once we come back, we will have tests on, and Wednesday we will revisit this chapter, okay, and see what else we can do in this chapter, finish it up, then we will move on with the problems and reviews, okay. So if you are missing some part of this chapter and you think she's going very fast and, oh, I didn't get that, it's okay. When we come back, we will have enough time to go over these concepts again, okay. I am taking you to a point where, if you want, okay, that you have touched these concepts in the class. Yes. 2 questions.
The rolling friction is where the tests stop. Yeah, that's what I was going to say. Like, at what point in our notes did our...
No, what we did in last lecture, what we did today is not included in the test at all. We stop at statics. Okay, even in statics, there is one topic that is stability, and one last topic, I think, related to the balance in the objects. We have not covered that. So if you have not seen it in the class, it's not on the test. Okay?
So we're not going to cover stability on the test?
Not on the test, yes. Not on the test. Not on this test.
Okay. So this test goes through chapter 9?
Through chapter 9, yes. And not everything in this chapter 9. Okay? So chapter number 7, 8, and 9, and in chapter number 9 we have done 9.1, 9.2, 9.4, and that's it. Okay, we have skipped stability, which I am going to cover with rotational motion at some point, but right now it's not included on your test. And chapter number 10, don't even look at it. You can revise it, but not for the test prep. Well, you are free to look at it because it's also not too far. Angular momentum. This is the last quantity, physical quantity, which we are going to go over for rotational motion. Just like the linear momentum, when the object is rotating, there must be angular velocity, and when there is angular velocity and mass, there will be angular momentum too. Angular momentum is represented as capital L I omega. What is I? Since again, we are replacing everything which was related to mass by moment of inertia and speed by angular velocity. So here, this is in linear momentum, we used to have a mass here and we used to have a velocity here. This time, it's a rotational motion, it's I and omega. The unit for I is kilogram into meter square. Unit of omega is radians per second. Or by putting them together, kilogram meter square per second. Okay, for any rigid body or any shape. Okay, so if you are talking about a, let's say a disc, any irregular shaped object, you will take the moment, its angular momentum as L equal to I omega. We need,
Sorry, what did you do with radians?
radians, even if you don't write it with it, it is there.
So it's just like understood.
Because it's angle, yeah. It's for angle, yeah, it's understood. I mean, you can put it in there.
No, I was just wondering, I was like, why?
I know. Linking it to torque. Torque, we know that it's equal to I alpha. Alpha, we know it's equal to delta omega over delta t. Now I is constant, right? That's like a mass. So we can treat it as a constant quantity. Taking I inside this delta, right? Because even if I put it inside delta, it doesn't matter because I is constant. Delta is only applied to omega. That is what it is changing. That takes you to this equation, delta L over delta T. That is the momentum form for torque. And does it look like any equation you have seen before? Velocity, do you remember seeing rate of change of momentum? So if there is momentum applied and rate of change of momentum is equal to the torque. Rigid body with respect to, this is for with respect to any axis, is sum of all torques about the same axis. Okay. So when linear momentum changes, that means force is applied on it. When the angular momentum changes, that means there must be torque acting on it, and rate of change of angular momentum, that should be equal to all the torque, sum of all the torques acting on it. Now this is the case when you have a rigid body, okay, like a sphere, disc, a ring. But if you have a single mass, the formula changes. If you have a single mass going about an axis, rotational axis, and it is at distance r, we can write its momentum in the direction of its velocity. We know that the linear velocity would be along the tangent at any point in that curved path. So taking the momentum with this velocity, we can write the equation for angular momentum. That would be equal to mvr. Where m is the mass, mv is the momentum of the object multiplied by the distance. Okay, in this case, when p and r are perpendicular to each other. Otherwise, this would be equal to mvr sine of phi. Okay, generally, if P is making an angle phi, then if it's not 90 degree and it's making any angle with the horizontal, then this would be a general formula for it. Okay, now if phi is 90 degree, I plug in 90, that becomes mvr. All right, in that case, momentum can have the two components to it. So I have a lot to talk about angular momentum. The angular momentum is not finished yet. Okay, there are a couple of demos that I would like to do. There are a couple of examples that I would like to go over. Okay, I think we ran out of time. I would not like to keep you here. Good luck for the test, and you can always reach me through the email. Okay, if any one of you plan to study during the holidays, you can always ask me to set up a meeting time. Okay, so I don't have big plans for these holidays. I will be available, but you have to let me know ahead of time that I want to have a Teams meeting. Okay, and I'll set it up for you.